Muy bien, ¿qué tal? Muy buenas tardes a todos, a todas. Esperamos que estén muy bien. En nombre de la Pontificia Universidad Católica de Valparaíso y en especial de la Escuela de Ingeniería en Construcción, le damos la más cordial bienvenida a esta última charla dentro de nuestro ciclo webinar de Madera, Estados Unidos y Chile, que hemos organizado en conjunto con SEC, la Soft Good Export Council, y que también ha tenido el apoyo de otras asociaciones y universidades como IAPS, el Comité Técnico de Puentes de Chile, la Universidad British Columbia, IAPMAS y Lonza Quimetal, entre otros. Hoy tenemos el gusto de poder tener una presentación muy interesante sobre puentes modulares de madera con nuestro expositor Paul Gilham de la Western Good Structure. Como siempre, comentarles y agradecer que durante la presentación mantengan sus micrófonos apagados y dentro de lo posible también la pantalla para que mejore la transmisión de los datos. Así también, durante la presentación ustedes podrán realizar sus consultas a través del chat, la plataforma del chat, la cual será finalmente serán presentados a nuestro expositor para su debida respuesta. Bueno, como les decía, agradecerles su participación y dejo con ustedes a Enrique Escobar, quien nos dará la presentación, nos dará, perdón, la introducción de nuestro expositor y también de nuestros amigos de SEC. Enrique, por favor.
Buenos días, no sé buenas tardes, no sé si me escuchan. Eh, es un agrado estar con ustedes esta tarde y poder presentar a Paul Gilham. Paul es el ingeniero jefe de la empresa Western Wood Structures, que estuvo en Edifica tiempo atrás, en el año pasado, junto con Hazen Highland. Y bueno, es un agrado para mí poder presentar una compañía que he conocido en mayor profundidad y que tiene una enorme expertise en el uso de madera laminada en estructuras y madera aserrada en estructuras. Y Paul nos va a presentar cómo se construyen estos puentes modulares modernos, que ciertamente pueden ser traídos a Chile en contenedores y que tienen mucha eficiencia en materias de transporte. Dicho eso, eh, también quisiera aprovechar de agradecer a la Universidad Católica de Valparaíso y al Software Export Council por haber realizado este ciclo de seminarios. Vamos a seguir todos juntos en una plataforma que vamos a armar para poder seguir materializando estos esfuerzos en torno a potenciar el uso de madera en infraestructura vial en Chile, que es algo que realmente requiere mucho trabajo. La universidad ha ido adquiriendo un liderazgo nacional desde la región de Valparaíso, como fue publicado recientemente en el Mercurio de Valparaíso. Y bueno, quiero agradecer a ellos, también agradecer al Software Expert Council y nuestra amiga Rose Braden es su presidenta, les va a dar algunas palabras para explicarles por qué estamos haciendo esta actividad y qué es lo que se espera de ella. Rose, can you pitch in and join us?
Thank you, Enrique.
Thanks.
Thank you all for attending today. This is the last in our very successful series talking about timber bridge technology, design, testing. We've had great attendance along the series, and Matthias will talk about the next series that will take place at the end of this webinar. We know that interest in timber bridge technology in Chile is great, and we also have attendees from other South American countries. So we're happy to have this level of interest in this technology, and we're pleased to, the Softwood Export Council is a nonprofit U.S. lumber promotion and education association made up of lumber grading agencies, universities, and state trade economic development departments. So what we do is we share information around the world about timber construction and furniture design using US species. And so please visit our website, softwood.org, if you'd like more information about species and applications. We're happy to be partnering with PUCV on this and other activities in Chile. Thank you.
Thank you, Rose. Now it's the turn for Paul to join us. And Paul, can you start your presentation? Thank you so much. Um, we are all ears.
Okay. So you can see the screen now?
No yet, but it's working.
Okay. Well, thank you for attending and inviting me to present. My topic is modern timber bridges. I have worked in the timber industry for 38 years, mostly designing and supplying.
Sorry, Paul. Paul,
yes.
it's not sharing the screen yet. Sorry, it's I'm not it's not yet.
Okay.
Can you try again, please?
Okay, let's try this. Screen share. Okay,
Good.
can you see that?
Yeah.
Yes, we
Great.
can.
Yeah.
Okay. Now, do you see the full screen?
Yeah,
Do you see
please.
the full screen?
No yet.
Yes.
No,
No, not yet.
it's not in the presentation screen yet. It's just
Okay, I was afraid of that.
F5 or
Well, I have it on F5. I have two monitors, and the right monitor has the screen on it. But I think you're looking at the left monitor, are you not?
Polly, if you want, I can turn my presentation, and I will follow
Yeah,
your
let's do that.
guidelines.
Let's do that.
Okay.
Yeah.
Hold on, just a second. I'm gonna do this here, and
please, Paul, you can stop the share screen, please, in order to Enrique could share. Thank you.
can you see this?
Yes.
Good.
Yes.
Okay. Next slide. Let's skip these two. Next. Next. Okay. So the learning objectives on this presentation include introducing the concept of modern timber bridges. You'll learn how enhancements to strength and durability make modern timber bridges suitable for most bridge applications. We'll examine several timber bridge types and discuss their benefits and limits. Finally, we will discuss the requirements for specifying a modern timber bridge.
That was a translation of what you just said.
So the common perception of timber bridges is that they are limited to small trail bridges for light use or a garden bridge that can be ordered from a catalog. But several developments over the last 50 years allow us to go beyond these types of structures to bridges that are suitable for major highways. By developing new methods of construction and new materials made from our timber resource, a new generation of timber bridges has been emerging that meet all of today's strength and longevity requirements for bridge construction. These bridges are referred to as modern timber bridges. Next.
Oops.
Here we go. So timber bridges have several advantages, such as a high strength to weight ratio, making timber bridges significantly lighter than bridges made with other materials. Modern timber bridges have a 50 to 75-year life expectancy, and we'll examine the procedures employed to achieve this level of durability. Modern timber bridges are prefabricated before preservative treating, which greatly speeds erection times. These bridges are delivered to the job site like giant erector sets. The members are lifted into place and simply bolted together to form the bridge structure. Timber is not affected by de-icing chemicals, which can detect efficient and are not required. It reduces the maintenance requirements when compared to other materials. Timber is the only renewable building material. In addition, the energy used to produce timber is significantly less than producing steel, And the amount of air and water pollution produced in manufacturing of timber is far less than steel and concrete. Timber bridges are competitive with steel and concrete on a cost basis, especially when the cost of the smaller foundations is considered. No other building material has the inherent warmth and beauty of wood. The variation of tones and grade patterns make wood desirable for finishes, also enhance the beauty of a timber bridge. Next. There are 6 major improvements that have been implemented in the design and construction of timber bridges that enables them to meet today's requirements for strength, longevity, while maintaining the charm and beauty that are inherent in timber construction. These 6 concepts. First is the use of glue laminated timbers or glulam. Glulam members are made with 50 millimeter thick and between 100 millimeter and 300 millimeter wide laminations together with waterproof adhesives to form longer members. These members are significantly stronger than solid sawn timbers. Go to the next slide.
Trying. Hold on, just a second. There it is. Just one thing at the bottom. At the bottom, you have the Spanish translation. At the top is the English original text. Abajo tienen la traducción de lo que Paul señala arriba. Okay.
Okay. Using glulam. Well, I was going to go through this. We'll get to that in a minute. Okay. We use waterproof adhesives that conform to the standard D2559 of the American Society of Testing and Materials. And the bonds that we make are actually stronger than the wood. It's an efficient use of the resources in that the high strength material is only placed where the stresses are high. We have the ability to manufacture long members up to 35 meters long, and the ability to curve the members so we can introduce camber or arches. Next. In a glulam plant, the lumber comes in, it's dried and graded. Next. The individual laminations have a finger joint. You can see it right here being cut into the end of the lamination. And then next. Those joints are assembled end to end to form laminations as long as the member needs to be. Next. In the last step, face bonding adhesive is applied to the wide faces. Next. And then the members are locked up in these clamps for the glue to set. Once the glue is set, again, the bonds are stronger than the wood itself. Next. Go back one. Thank you. So part of the concept of using modern timber bridges is that we use the same highway design codes as any other building material. So we're on a level playing surface with both steel and concrete. Next. In the United States, timber bridge design is governed by AASHTO, the American Society of State Highway and Transportation Officials, and they are currently using the load and resistance factor design method, or limit states. And their design vehicle is this HS20 vehicle, which is 320 kilonewtons. It weighs 320 kilonewtons. And okay, so that AASHTO specifies that loading. AASHTO also specifies the how wide the lanes have to be, how loads are distributed to the individual structural elements, and things like wind and seismic loads. Next. So this is a truck on a normal bridge. This bridge probably has 8 or 10 longitudinal girders underneath the pavement. AASHTO assigns a certain amount of the weight of this vehicle to a single longitudinal those members. It's the same distribution factors for wood as it is for steel or concrete. Next. One thing we're noticing when you're driving down the freeways that trucks just keep getting bigger and bigger. Sometimes, well, as I mentioned, the standard truck is a 320 kilonewton vehicle plus a lane load, which is 9.3 kilonewtons per meter. And that combination of lane load plus an individual truck accounts for the vast majority of loads that are applied to bridges. This is all specified in the AASHTO specification. Next. Also required in the US for new bridges are crash tested rail systems. This timber rail system here is designed to take the impact of the truck hitting it. And not only must it be designed not to break, but it has to have the right geometry so the truck doesn't roll over the rail, and that when it reflects back into the road, it does not cross into oncoming traffic. Next. Not only are timber bridges used now for vehicle bridges, but also for pedestrian bridges. AASHTO LRFD guide specifications for the design of pedestrian bridges is one of the two design specifications that we use. They require a 90 pounds per square foot, which is 43 kilopascals for the pedestrian live load. Again, wind and seismic loading is governed here. And then unless access is prevented for other vehicles, a 6 to 10 foot wide bridge has to be designed for a 10,000 pound truck. If it's over 10 feet wide, it has to be designed for a 20,000 pound truck. Plus, there are requirements for the rail heights and the rail spacings and the loading that the rails must withstand. Okay, next slide.
That was the translation.
Mm-hmm.
Okay.
Okay, there should, yeah, or structural engineering analysis. And we break that down into four categories. The first is the use of computer aided design. And using the computer, we're able to optimize the design and greatly increase the effectiveness of our design. What used to take 2 or 3 days now can be done in a few hours. Because we have that extra time, we can optimize the design by removing material where it's not needed and only putting the high strength material where the highest stresses are. And we can identify locations in the design that might have issues with them with the analysis software. And as I mentioned, it greatly reduces the time. Next. This is a typical bowstring truss. This is in a bridge not far from our offices here in Portland, Oregon. And this is it's about a 45-meter bridge. And this is a bowstring truss. The yellow is tension on the bottom cord and the red is compression on the top cord. Historically, trusses were analyzed using classical truss techniques, and you would come up with these axial forces on the webs and on the cords. Next slide. But you would not see these bending moments that are a result of the continuity of the members. And you'll see down here at the heel, you have very large moments. And when these trusses have issues, usually it's right down here on the ends. So we can see that in the analysis and appropriately design this region to withstand this load. Next. We use computer modeling and fabrication detailing. So we use computer-assisted drafting. We can use solid modeling of the individual members, and then we have the ability to interface with fabrication equipment. Next slide, please. This is a bridge up in Washington, the state just north of Oregon. This is about 145 meters, I believe. That sounds right. About 145 meters long. And you can see how complex it is with a horizontal curve. It's got a slope, and we have all of these arch members and the bents. Every single one's different. But if you look at this bent right here, next slide, please. We can extract that from the model, and we have the bent fully laid out in the model. Next slide. From that information, we can make the fabrication details. This shows all the timber details so that they can actually fabricate each piece from the information from the model. Next slide. This is the connection of the vertical column element on that bent to the arch. And this is fully detailed in the solid modeling. Next slide. And then that can be extracted, and in this upper left view, each plate is extracted from the model, and so the steel fabrication shop can cut out these plates, weld them together, and we have the exact piece that we need. Next slide, please. So the next concept is plant prefabrication. Before modern timber bridges, it was not uncommon for a contractor to buy several truckloads of treated material, bring them out to the job site, and then cut them to fit the requirements at the job. However, when they did that, they through the treatment barrier and exposed untreated wood to decay organisms. So plant prefabrication, all of the cuts and all of the boards are done in the fabrication facility using the proper tools to fabricate these large members. These members are so big that you don't bring a beam member, if you will, to the saw and try to cut it. You got to bring the saw to the member. That's okay. We can be here. So in the plant, yeah, go ahead and go to the next slide. In the plant, the members can be all laid out and test fit. All the holes are drilled. All the end cuts are made. This is that same bent that we were looking at on that curved bridge. Next. We use steel templates to lay out the holes. Next. And then we use drill presses, and this drill press is actually an over-under drill press with a drill on top and a drill bit on the bottom. So the top one only goes down halfway, and then the bottom one comes up from the bottom, and so the holes are always aligned. You don't get any drifting of the drill bit through the member. Next. Oops, wrong way.
That's it, sorry.
There you go. Okay, in timber bridge design, modern timber bridge design, we are using modern preservative treatments. All of the treatments that we use are Environmental Protection Agency registered pesticides, and they are effective in the prevention of decay and insect attack, and they form a complete treatment envelope of each member. Next slide. So this is a charge of lumber ready to be pressure treated. It's separated by a sticker, so it has air on all four faces. And then this, next slide. This is loaded into the pressure treating cylinder, and several of these cars will be loaded with members and run in. Next slide. And then the pressure treating cylinder is sealed, and the preservative is pumped into this cylinder. And under pressure, the preservative chemicals are mixed with what's called a carrier. And the carrier can be water, it can be like a diesel oil, or it can be like a paint thinner, a very light oil. And those are put under pressure, and that pressure forces the mixture into the wood. And as it moves into the wood, the preservatives are designed to chemically bond to the wood fibers. Next. Once it's been pressure treated, it's rolled out to this area called the drip pad. And the drip pad, the members stay on the drip pad until they are done dripping and total fixation has happened with the chemicals, the preservative chemicals, and the wood. Next slide. This is a view of two different pieces of wood that have been pressure treated. The one on the left is a difficult to treat species like Douglas fir. And with these members, you can see these little knife cuts. That's called incising. And the incising allows the treating to go into the wood and then go with the fibers in the long direction and form a complete treating envelope. The member on the right is simply a species that treats more easily, so it doesn't have to have that machine incising. Next slide. Until about the 1990s, the treating industry was relatively lax about how much treatment they were putting in the members, and they figured that if the more that they put in, the better. But then they found out that they were having issues with the treating leaching out of the members and into the environment. So in about mid-1990s, this is 1996 on this particular cover, they came up with these best management practices for the use of treated wood in aquatic environments. And what this included was chemical minimization, product cleanliness, inspection and rejection, fixation, which is the total binding of the treatment to the wood fibers, field installation guidelines, and then quality control and certification. Next slide. So before the BMPs, or the best management practices, a piling treated with creosote might look like this one on the left. You can see that the treatment is leaching out into the environment, as opposed to the one on the right, which is treated with the best management practices, and it's clean and dry, and there's not excess that's going to leach out into the environment. Next one. So two recent studies by the U.S. Forest Service looked at two different conditions where treated wood was used over a sensitive aquatic environment. And the first one was this arch bridge up in Washington State. And the next one, next please, was this very long boardwalk in the state of Oregon. And again, in a very sensitive wetland environment. And the results of the first study included, these results suggest that there are minimal environmental risks associated with preservatives lost from timber bridges. The conclusion of the second study concluded that no plant or animal species were significantly reduced by the boardwalk treatments. Next one, please. The Forest Service has also come up with these guidelines for minimizing the preservatives entering the environment during the construction process. So there's lots of instructions for the contractors in order to make sure that they're not being careless with this materials, but they're collecting all of the debris. Okay, so we're going to look at several bridge types. Next slide, please. We're going to look at several bridge types, and these are from the shortest to the longest, and some of them are specifically for pedestrian use and others are for vehicle use. So the first one is boardwalks, and boardwalks are typically short bridges connected end to end, and they're used often in sensitive wetland environments where you don't want a lot of disruption of the soils. Can you go to the next slide? There you go. So shorter spans, maybe 2.5 meters to just under 4 meters. They have very light, pure foundations, so they don't disturb the soil of these sensitive areas. Next slide. And they look something like this. You have your rail and post system, you have your decking, you have your longitudinal elements, and then you have many of these little posts sitting on a concrete block that supports it. And there's very little disruption to the sensitive landscape. Next one. The beauty of these is that with some care in the design, you can make these fit through a site that has many obstructions like these trees. And in this one, you've got this nice curved look. Next one. So this one is a very long boardwalk in, this is the Puget Sound region of Washington. So this is tidal zone right through here. And the water comes up just to the bottom of these cross bracing, of course, every 12 hours. And this particular bridge is about 1,700 feet, 1,700 meters long. Next one. And because these supports are so close together, they can be installed on very lightweight foundations. Here you can see small timber piles on the left, and then these are helical anchors on the bridge on the right. So again, very lightly loaded foundation systems without disruption to the, in both of these, they're not using any kind of pre-excavation of the site. Next one. Another method are these diamond piers. These pipes are inserted through this concrete block, and the pipes are actually acting as spread footings, if you will. And these have very small disturbance, a couple shovelfuls of dirt for each foundation only. Next one. Okay, the next is longitudinal deck bridges. These are typically used for vehicular bridges, and they can go from about 3 to about 12 meters in length. They have very low clearance requirements. They're made from glue laminated deck panels, and they have very easy installation. Next slide. So this is a longitudinal deck bridge, and you can see this deck panel here. Go to the next slide, please. Each of those deck panels is 18¼ inches deep. So from the top of the deck panel to the bottom, 18¼ inches. And in this case, they're about 42 inches wide. So if you would think of a beam, 18¼ inches deep by 42 inches, no, I'm sorry, 18¼ inches wide by 42 inches deep, laid on its side, and then you put 3 more next to it, and that builds a bridge. In a sense, it's a slab bridge. The post and rail system here is a crash-tested rail system, and so this meets all the requirements of the of AASHTO. Next slide. Girder bridges are probably the most common of all bridge types. In them, we use longitudinal girders with transverse deck panels, and they are efficient up to about, what would that be, 24 meters or so. After that, we look at a different type. But if you'll change the page, next slide, excuse me. So here is a pedestrian bridge that is a girder bridge. You can see the girder on the bottom spans from foundation to foundation, transverse deck panels on top of the girder, and then just a post and rail system. Next slide. When you're standing on the bridge, it looks like this. We like to use glulam deck panels. They're very consistent in their thickness and they wear very well. Underneath the bridge on the right-hand picture, you can see the lateral force resisting system. We have these horizontal trusses that will resist the wind and seismic loads. Next slide. This is a 3-span vehicular bridge. This span in the middle here is about 18 meters, and on the outside, I think those are about 15 meters. And this is for a single lane vehicle. Next slide. As you can see, all of the connectors are in pre-fabricated, in this case, these routes up here for the deck clips. The holes for these machine bolts are all drilled ahead of time, like out on the post, at the post bracket and so forth. So all the fabrication, as I mentioned, is done before the members are pressure treated. So around each one of these holes, there's quite a bit of pressure treatment because so much of the wood was exposed when the members were treated. Next slide.
Let's translate in there. Okay.
This is that same bridge with a load of crushed aggregate backing across the bridge in order to fill up the far abutment. But I wanted to show you that these can carry heavy loads. That's about a 46,000 pound vehicle. Next one, next slide. The next type of bridge is what we call a side girder bridge. And in this, it can be used when the clearance below the bridge is very limited, like there might be a creek that is does not have very high banks, or it could be a bridge that goes over a roadway. Again, spans up to 18 meters or so. Is that right? No, longer than that. About 25 meters. Okay, next slide, please.
Right.
So here's a bridge with very low clearance underneath the girders. And you can see the girders are pretty tall. If the deck had to be attached to the top of the girders, you'd have to have a significant fill on both ends. Next slide. But in this case, you can see that the deck is placed down below the top of the girders. So the distance from the deck to the bottom of the girders is relatively small. That way you can maintain the clearance below the bridge that's needed. Next slide. Truss bridges, we use these when they get longer than about 85 feet. And hang on a second. 85 feet is about 26 meters. And these will go up to about, actually we've gone 280 feet now. So we've built these up to 85 meters long. The members are lightweight. There's significantly more fabrication and connecting steel. The erection procedures are more complicated, but we can make very long spans. Next, please. This is a 30-meter, we call this a pony truss. The truss, the top cord acts as the rail for this bridge. This one is about 30 meters long and about 2.5 meters wide. Okay. Next slide. This is a bowstring truss bridge, 135 feet long, which is 41 meters. And again, it's for pedestrians, and it goes over this roadway down below. Next. Another type of bridge, truss bridge, is we call a parallel cord truss. And as you can see, the top cord is way higher than the decking on this one. So we can brace the top cord in between the individual trusses, and we don't have to have any kind of knee braces extending out from the truss. Next slide. This is another parallel cord truss. This one is underneath a bridge. This is in California, and it's 45 meters long. 2 lanes of traffic, carries vehicular and pedestrian traffic both. Next. This is a combination of a bowstring truss and a parallel cord truss. This is a three-span bridge. The side spans are 105 feet, which is 32 meters, and then the main span is 200 feet, which is 61 meters. Again, it's a pedestrian bridge. Next slide. And this is the 280-foot one that I was mentioning, 85 meters long. It's up in Portage, Alaska, so it has some pretty severe environmental lots of snow, lots of wind. This particular one uses Douglas fir truss members, but the rails and deck system are made out of Alaskan yellow cedar, which is native to Alaska, and it's naturally decay resistant. So the deck and rail system doesn't have to be pressure treated. Next slide. Okay, arch bridges, again, go from about 30 meters to 60 meters. The members are larger than trusses. There's no actual truss action happening on these. They take less fabrication and connecting steel than the trusses, but the erection procedures are significantly more complicated because you're lifting longer, heavier members. Again, the arches can be above or below the deck. And because arches have an outward thrust on them, the foundations can be more complicated. Next slide. So this is a arch bridge with the arches over the deck in California, 55 meters long and about 6 meters wide. And it's designed for vehicle traffic. As you can see, we have one of our trucks on it. Next slide. And just real quick, a couple slides. You can see the heel assemblies here. He'll be bringing these two holes together and driving a pin through. Next slide. There you can see the pin already assembled. Next slide. We have vertical hanger rods, horizontal floor beams, and then we're using a longitudinal deck system for the decking. And the decking is multiple span. You can see the one on the left and the one on the right is a 3-span member, and this middle one is a 2-span member. Next. This is actually 2 bridges, end for end in the state of New Jersey. And these are 43 meters long and about 9 meters wide. So they have 2 lanes of traffic on the bridge, and then they have these pedestrian bridges outside of the arches separated from the traffic. Next. These are those same 2 bridges when they were installing the asphalt wear surface. Just wanted to show you that you can put asphalt on these and that it will withstand the heavy construction equipment as the asphalt is being applied. Next. Here is a arch bridge with the arch underneath the the walkway. Next slide. And this is the same one that we looked at with the solid modeling. This one is in Washington. It's almost 400 feet long. Let me help you out here. 121 meters total length. And it's a pedestrian bridge.
Sorry.
Go ahead, next one. And you can see the horizontal curvature to this. So we actually curved the deck panels to match that horizontal curve. Next. And this is an arch where the arch is halfway below and halfway above the walkway surface. And you can see the walkway system is very thin. There's not very much depth to the members on this one. Next one. Suspension bridge, either a catenary, suspension bridges with either catenary or cable stayed can go up to over 400 feet long. We've got one that I'll show you that's 475 feet. The members are very small. The cable and the tower designs are significant. And you have to have a cable anchorage to the foundations for the longitudinal elements. Next, please. So this is a pedestrian suspension bridge in Virginia in the United States. Next. This is a pedestrian cable stay bridge, and this one is in Yamato City, Japan, and it's 53 meters, excuse me, end to end. Next. And then this is the 475 foot or 145 meter Hiroshima Airport Bridge in Hiroshima, Japan. This is a 2-lane vehicle bridge. And so it'll carry your vehicle traffic. They've tested it several times with large trucks going across it. But it's concrete towers, cables, steel cable stays, and then the rest of it is all timber. Okay, next one. As I said, covered bridges are kind of a category in themselves. In this case, we have a horizontal truss covered with this timber roof assembly. Go to the next slide. Okay, I thought I had another one. This is a covered bridge that actually uses glulam arches to form the roof. And then it's just a longitudinal deck, longitudinal string or transverse deck bridge. Next one. And then here's another vehicle bridge with a parallel cord truss, a walkway on the outside, and again, vehicles down the middle. Next. Okay, so when you specify timber bridge, the things have to include are the length, whether the length is a clear span, center to center of abutments, if it's the out to out length and so forth. Got to consider the scour potential, 100-year flood elevation and stream protection when you're determining your length. The width is based on anticipated traffic. It's good to determine what building code is going to govern before you start designing it, because if you design in one code system and the approving agency uses a different code system, you will be designing it again. You can choose your bridge style. We just looked at several of those. You can change the rail configuration a little bit, add architectural features. And then we recommend a pre-qualified bridge supplier who will supply calculations and shop drawings stamped by a professional engineer. And then we require certificates of conformance for all the materials, for the glue lams, the steel shapes, the hardware, and the preservative treatment. And then the foundation design can be designed by a consultant or a bridge supplier. Next. Okay. So in summary, Timber bridges, or modern timber bridges, combine the use of glue laminated timbers, the most recent highway design codes, computer-assisted analysis and detailing methods, and environmentally appropriate preservative treatments to provide structures capable of carrying today's design loads and durable enough for a 75-year life expectancy. We looked at several types of bridges, and we talked really quickly about how you specify one, what's required to specify a timber bridge. Next. So if you have a little 6-meter garden bridge, or up here you can see this vehicle bridge, that one's about 20 meters, or a 145 meter vehicle bridge, which is really the landmark of this park. You can do it in timber, you can do it beautifully, and it will last 75 years. Thank you.
Gracias.
Thank you, Paul. It was a really, really great presentation, an overview of all bridge, this kind of timber bridge, the different typologies, or that is very useful for Chile and I suppose also Latin America, because you can show the different alternatives that we have to build, design and build bridges, not only our traditional girder and slab bridges. So we have several questions, and let me start with a question of the Vladimir Pasmiño. He asked about of the nominal resistance of the laminated good for compression and also for tension. Do you have? Yes.
Yeah.
Sure.
So the allowable strength for wood is established by the trade organizations. They run a number of tests for each grade of wood, and then they assign the allowable stresses based on the test results. It's an ongoing process, and it has a lot of statistics in it. But for instance, I just finished a job up in Canada, and the allowable bending stress was 30.6 gigapascals. So in English units, that's about 2,400 psi bending stress. It's not as strong as concrete, and it is not as strong as a stress as steel or concrete, but it's much lighter, and we just use larger members in order to achieve the strength we need. So a steel beam is going to be usually what we call a W shape. Some people call it H shape. So you have a flange top and bottom and a web. And the design of the steel beam itself optimizes the use of the resource by concentrating most of the steel in the flanges. Well, in wood, we do that a little differently. We put the high grade members in where the tension and compression stresses are, and in the middle of the beam where the stresses are lowest, we use the lowest grade. So in a sense, we're making an H beam just like steel, but it's we do it by changing the strength of the material, not changing the size.
Mm-hmm. Great.
Sorry, the figure was la cifra, the modulus of elasticity for Douglas Fair Glulam is about what? I didn't hear that well.
It's about well, for glulam, it's about it's 1.8 million pounds per square inch, and I don't have the conversion off the top of my head.
Okay. Don't worry.
Yeah,
it's huge.
It's so concrete's going to be around 3,000 3 times 10 to the 6th. We're about 1.8 times 10 to the 6th. So just underneath concrete. Steel is significantly stiffer.
Mm-hmm. Paul, there are another question. In this case, Mario Yañez is asking about of the maintenance plan for this kind of road bridges using wood, because what happened when we have bridges with 25 years old or maybe older than that? So you can recommend something about of that?
Yeah. So the main thing to look for on timber maintenance, and it's usually after the first year of service, is that the wood is going to shrink a little bit as it dries out. And all your bolted connections are going to become a little bit loose. So after the first year, when the wood has reached equilibrium, the bolts need to be tightened. After that, a thorough inspection about every 5 years to see if there's any checking that's happening, or or if there's any kind of mechanical damage, say that somebody runs into the rail or so forth. But the wood itself should not have any issues if it's properly treated before the bridge is installed. So with the proper treatments, we're finding that we get about a 75-year life expectancy.
Mhm.
The very first bridge I showed, the arch bridge over the roadway, that was built in 1968. They just completed an inspection of that and it got a glowing review. So we know that if we properly fabricate the members first, then we pressure treat it, and then one of the keys is keeping it clean. Um, it'll last for at least 75 years.
Mhm. Paul, let me link with another question that is
Mhm.
of Paula Montes asking is about of the preservations. You know, you talk about of the pressure with CCA,
Mhm.
and of course you talk about of good of United States. Do you think that it's possible to, you know, apply an alternative of preservation systems and also an alternative of this kind of goods? Considering that time of maintenance and durability?
So in the United States, we use both waterborne preservatives like CCA, ACCA, ACZA. Those are the three main waterborne preservatives. And those are typically used in southern yellow pine, because southern yellow pine can be treated thoroughly. And so they treat it, they take it to the plant, they clean it, and then they glue it. And they get treatment fully through each lamination. So there's no place for any kind of decay to begin or insect attack. So that's a combination of waterborne preservatives and southern yellow pine, which is a readily grown in southeast United States. Uh, Out where I'm from, on the west coast of the United States, we grow mostly Douglas fir, and Douglas fir and southern pine are pretty much equal in terms of strength. But Douglas fir does not treat as easily as southern pine, so we machine incise it, and we do all of the pressure treating after the members are glued up. So southern pine with the waterborne, you glue the laminations and then make the beam. With Douglas fir and oil-borne preservatives, we make the beam and then pressure treat it. So you have to have an appropriate treating system for the species of wood that you're using. And I believe in Chile, do they grow, is it red
Oregon
pine?
pine, or Oregon pine, national Oregon pine,
Yeah.
that produced
So
in the south
that's,
of Chile. Mhm.
yeah. So that would probably be appropriate for um, the waterborne preservative, re-dry it, glue it up together to make the glue laminated members. Um,
Mm.
and do you also have radiata pine?
We have mainly radiata pine. That's our most common lumber for construction purposes in Chile. And
Yep.
we have so-called Douglas fir, which is so-called Pino Oregon, which is produced in the south of Chile, but it has no standard of resistance. It's not ranked as you do.
Okay. Yeah.
Para todos nosotros, en Chile el pino radiata ciertamente es el material más usado en construcción, y existe un pino Oregón que está en el sur de Chile, que es un pino traído de Estados Unidos, como el Douglas Fir. Carlos Granier, que está por ahí, o algún ingeniero forestal podría explicarlo más en lo que es su origen, pero el problema es que no está, la industria en general no lo entrega graduado mecánicamente, como se hace con el pino radiata o ciertamente el pino Douglas Fir en Estados Unidos. Perdón por mi intromisión, pero...
Okay, Paul, unfortunately we are in the limit of time, so just to thank you again. It was a really great presentation. It's very useful especially for Chile, in order to open our eyes to see everything. So thank you again. Y para todos, bueno, con esto vamos terminando nuestra sesión de webinar. Permítanme, eso sí, un minuto para comentarles algunas actividades, porque si bien termina nuestro ciclo webinar aquí, tenemos como Pontificia Universidad Católica de Valparaíso y también con colaboración de nuestras asociaciones amigas, una serie de actividades. La primera que quiero destacar es, espero que se vea allí, una serie de cursos que están relacionados con esta área. Son cursos del área de puentes. Vamos a tener 3 cursos de puentes tradicionales: puentes vigas, losas y cajón, que comenzamos el 20 de noviembre de este año, una sesión de 12 horas, y donde también incluiremos, por cierto, el tema de la madera, puentes de madera. Luego, el 11 de diciembre, comenzamos el curso de diseño de puentes según manual de carreteras. Veremos allí cálculo, análisis estructural de puentes tradicionales chilenos. Y cerramos este ciclo en el curso de puentes soportados por cables, segunda edición. Ya tuvimos la primera en agosto. Esta de segunda edición será el 8 de enero y veremos puentes colgantes, atirantados y en arco atirantado, como muy bien Paul aquí ha mostrado. Así que los dejamos cordialmente invitados, por si están interesados, a ir a icc.extensión@pucb.cl. Enrique, agradecerte a ti por este tiempo. Thank you to Rose, SEC, and all of our association that is supporting all of this activity. Y bueno, Enrique, unas palabras al cierre, si te parece bien.
Sí, no sé dónde está mi video, si está visible o no, pero
¿No estás
parece que sí.
compartiendo? Si quieres puedes compartir.
Start video, ahí está. ¿No se está compartiendo mi video? Pero ¿me escuchan?
Sí.
Sí, me escuchan, no sé por qué no se ve el video mío. Bueno, quiero agradecer a todos ustedes por la maravillosa oportunidad, particularmente a ti, Matías, que has creído en esta iniciativa, que hablábamos largamente en distintos lugares, en Valparaíso, en el Café de la Moneda, etc. Y logramos en el Ministerio de Obras Públicas crear este seminario que iba a estar orientado primero al Ministerio de Obras Públicas y después se amplió. Entonces, gracias. También quería agradecer a SEC. Thank you, Rose, for all the support. Without you, this could not have been possible. And all the companies that belong to SEC that in a way have, and institutions that have pitched in with her knowledge, expertise. Thank you so much. And we invite you to remain connected. Los invitamos a seguir conectados porque tenemos trabajo que hacer, Matías, en este sentido. Muchas gracias.
Así es. Estén atentos, ya contamos con sus contactos, así que tendrán noticias nuestras, sea para webinar, sea para cursos o para alguna otra actividad en la cual podamos impulsar el tema de la madera. Así que a todos, que estén muy bien, muchas gracias por poder asistir a todas estas charlas y nos estamos viendo muy pronto. Cuídense.
Gracias.
Gracias por la invitación.
Thank you to everyone.
Gracias, que también.
Bye.